Hello and welcome to EFM Electronics for Makers. I'm your host Rob Mitchell, and in today's video we're going to be looking at the MitchElectronics 555 Monostable kit. Now, in a previous video, we looked at the other MitchElectronics kit, the 555 A-Stable, and this is a kit that allows you to turn a 555 IC into an A-Stable oscillator, which is one that switches from on and off repeatedly like a clock and can be used for many different applications. And we also looked at the internals of the IC, how it works and why the A-Stable actually works. Now, this here is the Monostable project. Now, this one's different because it is monostable, which means it's only stable in one state, the off state. A small tactile switch allows you to set the 555 into its monostable, unstable state, in which case the output goes high for a short period of time, but eventually comes back to off to remain in the stable state, hence mono or one stable state. But how does it really work? Now, a lot of monostable explanations out there will talk about the external capacitor and resistor, which are the key critical components to making the thing work, but doesn't truly explain why the circuit actually works. In order to understand this, we have to look at the chip itself. But before we do that, let's have a quick look at the 555 itself. Now, one of the really cool things about the 555, as we discussed in a previous video, is that it dates back to the 70s, and despite the fact that it is more than 40 years old, it is still produced in the billions each year, still used in many millions of devices, and still available in DIP packages. Now, it strikes me as just quite frankly amazing that a chip, a simple timer chip, which you would have thought would be sort of made discontinued years ago, is still popular and still used. And it's one of those reasons why it makes it a sell. It's one of the most popular sort of projects out there. It's one of the first ICs most people are introduced to is the 555 timer, and quite frankly for right reasons. So the 555 monostable circuit by MitchElectronics is a great demonstration as to how it works, and one of the nice things about the documentation is that it talks about the internals of the chip as well and why this thing actually works. So let's get to some paper and find out what makes this actually work. So before we actually talk about how this thing works, we need to set some starting conditions, which will describe what this circuit does when it's in the stable state, which is the off state. Now, in the off state, the voltage across C1 is 0 volts. Since the voltage across C1 is off, or 0 volts, the voltage at 7 and 6 will both also be at 0, which means this one will be at 0 and 7 will also be at 0. So the discharge, nothing's going through the discharge because the discharge transistor has already discharged C1. And we also find that since 6 is also connected to 0, then this one's connected to 0, which means the positive is smaller than the negative. So the output of comparator, we'll call this comparator, let's say comparator 1 is 0 volts. Let's call this comparator 2. Now, what we also find is that the trigger pin, which is pin 2, is held high by a resistor, R1. When the button is not pressed, 2 is kept high. That means the trigger pin 2 is at 9 volts, or plus V. In this case, plus V is 9 volts because we're powering it with a 9-volt battery. And so what we find is that if trig 2, or the trig pin, which is pin number 2, is high, then the negative pin here is higher than the positive pin, which means comparator 2's output is also 0 volts. Now, as we're doing starting conditions, we'll also assume that the starting condition for this internal flip-flop in the 555 is set to reset. So reset will be triggered, which means the output of Q will equal 0. But because the output is 0 from Q, it gets inverted by this little inverting output, which means it goes to 1, so it keeps this discharge transistor operating, so the capacitor C1 can never charge. So what happens when we push the button? Well, when the button is pushed, this pin here, trigger 2, which is pulled up by resistor R1, will go to 0 volts because we are going to short the current here straight through to there, So the current goes through R1 through the switch into ground. It doesn't go into 2, which means the voltage across S1 becomes 0 volts. The input to 2 will also be connected to 0 volts, and if the negative pin of the comparator 2 is connected to 0 volts because the negative input is connected to trig, what we find is that the positive pin on the comparator becomes greater than the negative pin, which means the output of this little amplifier goes to high, or 1, or 9 volts. And when that happens, we set the latch. And when the latch becomes set, that means the output of the latch becomes set. So Q becomes 1. Now, because the latch has an inverting output, this means that we've actually got a 0 volts here, which means the discharge transistor turns off. At the same time, it gets reinverted so that the output goes to 1. So if we draw this on a graph, what we find, if we put both signals on the same graph, those are time, and that's V. This top one is going to represent the trigger, and this this bottom one here will represent the output, and the top one represents the trigger. So when we push the trigger is normally 9 volts, and when we push it, it goes down, comes back up when we release. And what the output does is the output is normally off, but here it now switches on. When the output goes to high, that means the discharge transistor is turned off. Now, if the discharge transistor is turned off, that means current flows through R2, through RV1, which is our potentiometer, and this causes the voltage across C1 to start to increase. It starts to charge, the capacitor begins to charge, and when that happens, the voltage goes up. So what we get is a voltage across C1 looking like this. Starts to charge up. A typical RC charging curve. Now, because the capacitor is connected to threshold, or pin 6, eventually this pin will become greater than the voltage here. Now, if we're running at 9 volts, then this voltage here will be about 6 volts, because each one of these resistors is of equal value. And that means eventually the capacitor voltage will go slightly above 6 volts, and when that happens, the output of comparator 1 turns on. So now it becomes 9 volts. Now, we should also state here that because we only briefly push the button, the voltage at trig 2 will go back to 9 volts, which means that the output of comparator 2 goes back to 0 volts. And when this happens, we find that reset now equals 1. And that means the output of this flip-flop becomes 0. Now, when the output of the latch turns off, the output actually has an inverting stage, and so this part of the circuit turns on, or becomes 9 volts, which turns on the discharging transistor, at the same time turning off the output. And so we get this. The output goes down like that, and the capacitor discharges. Now, unlike the astable circuit, the monostable doesn't connect the charging capacitor here to pin 2. That means the trigger never gets triggered during the discharge phase, and so once the capacitor voltage reaches all the way down, the output remains off, and this is the monostable state, because no matter for how long time the universe could last for, this output never goes high again until you push the button again, and this is how the monostable works. Now, the length of time for which the output remains on is related to the value of C1, RV1 and R2. Now, in this circuit, you can find the equations online to calculate all of these. Now, the bigger R2, RV1 and C1 are, the longer the output remains high for, and if you make those values smaller, then the output of the monostable also reduces. And that is how the 555 monostable circuit works. Well, that's all we have time for today in this episode of EFM. Thank you for watching, and see you next time.